For data manipulation and visualization, this code imports pandas, NumPy, and matplotlib libraries. In addition, it imports torch and torch.nn, which are Python libraries for deep learning. Using the pandas library, the following code reads a CSV file named amzn. CSV and stores the data in a variable named data. It is likely that the CSV file contains information about Amazon's stock prices. Executing this code loads the data from the CSV file into your program, making it available for further analysis. Data is assumed to be a pandas data frame containing financial data, such as Amazon's stock price. Data date, close, selects only two columns from the data frame, namely date and close. The operation creates a new data frame containing only these two columns and assigns it back to data. In this code, you are filtering the original data frame to keep only the date and close columns, discarding any other columns. You can use this operation to analyze or visualize these specific columns. The code assigns a value to the variable name device based on the availability of a CUDA-enabled GPU, graphics processing unit. Torch.CUDA.is_available checks if a CUDA-enabled GPU is available. The device variable is assigned the value CUDA:0 if it is. GPU device CUDA:0 represents the first GPU available. A CUDA-enabled GPU is not available, so the value CPU is assigned to device, indicating that the computation will be performed by the CPU, central processing unit. Using this code, you determine which device, either GPU or CPU, will be used for PyTorch computations. If GPU acceleration is available, certain deep learning computations can be significantly accelerated. Matplotlib is used to perform data preprocessing and generate a plot. pd.to_datetime datadate converts the date column of the data frame data into a datetime format. Various time-related operations and plotting capabilities are enabled by this conversion. This code creates a plot using the matplotlib library by calling plt.plotDataDate, data close. An x-axis plots the date column and an y-axis plots the close column. Over time, the close column represents Amazon's stock closing prices. You can visualize and interpret the data by transforming the date column into a datetime format. This plot displays Amazon's stock prices over time, providing insight into its historical performance. To create a modified data frame, this code defines a function called prepare_dataframe_for_lstm. From copy import deepcopy as DC imports the deepcopy function from the copy module and renames it DC. The purpose of this function is to create a deep copy of the data frame, ensuring that any modifications made to the copied data frame do not affect the original data frame. Prepare_dataframe_for_lstm takes two arguments, df, a data frame, and n_steps, the number of previous steps or look-back period to consider. This function makes a deep copy of the input data frame, df, so any changes made within it will not affect the original data frame. This line sets the date column as the data frame's index, making it easier to manipulate and analyze data based on dates. To iterate from 1 to n_steps, inclusive, a for loop is used. df_close di, equals df_close. Shift I creates a new column in the data frame, representing close prices shifted by I periods. As a result, historical prices leading up to the current time step can be captured. The code df.dropNA in place equals true removes rows containing missing values, NS. The shifting of values creates NaN entries for the initial rows of n_steps. The function returns the modified data frame as its output. This line indicates the value 7 of the variable lookback representing the number of previous time steps to consider in the LSTM, long short-term memory. The line shifted_df equals prepare_dataframe_for_lstm data, lookback, calls the prepare_dataframe_for_lstm function with data frame and lookback value. A modified data frame is assigned to the variable shifted_df. As a result of executing this code, you create a modified data frame that includes columns representing historical close prices. The modified data frame can then be used for further analysis or input into an LSTM model for time series forecasting or analysis. The following code converts a pandas data frame, shifted_df, into a NumPy array. As shown in the code, shifted_df_as_np equals shifted_df dot to _numpy converts the shifted_df data frame into a numpy array using pandas to _numpy function. The function converts the data frame's values, including the index and column labels, into a two-dimensional array. Shifted_df_as_np contains the same data as the original data frame, but in a different data structure. NumPy's array operations and functions can be used to manipulate the array. This code generates a NumPy array representation of the data frame, which can be used to perform various numerical computations, apply machine learning algorithms, or utilize specific NumPy features and capabilities. The following line of code retrieves the shape or dimensions of the NumPy array shifted_df_as_np. An array's shape is determined by its .shape attribute, which is the number of rows and columns. Shifted_df_as_np.shape returns a tuple containing the number of rows and columns in the shifted_df_as_np array. In addition to understanding the array structure, this information can be used to determine the size and structure of the data it represents. By using its dimensions, you can programmatically access and manipulate specific elements or subsets of the array. A min-max scaler from the scikit-learn library is used to scale the NumPy array shifted_df_as_np. The line of code from scikit-learn.preprocessing import min-max scaler imports the min-max scaler class from scikit-learn's preprocessing module. Scaling numerical features to a specific range is commonly achieved using the min-max scaler. This line creates an instance of the min-max scaler class with a feature range of 1,1. By setting scaler equals min-max scaler feature underscore range equals 1,1. After scaling, the array's values will fit within a range of -1 to 1. The line shifted_df_as_np equals scaler.fit_transform shifted_df_as_np applies the scaling transformation to the array shifted_df_as_np. Scalar objects use the fit_transform method to fit the scalar to the data and then apply the scaling transformation to the array, replacing the original values with the scaled ones. With this code, the numerical values in the shifted_df_as_np array are transformed and scaled to fit within the specified feature range. In machine learning tasks, scaling features to a specific range can improve the performance and stability of certain algorithms, especially those that are sensitive to scale. It is then possible to analyze or model the resulting scaled array, shifted_df_as_np. A data split is performed on the shifted_df_as_np array to separate the input features, x, and the target variables, y. The line of code x equals shifted_df_as_np, 1, extracts the input features from the array shifted_df_as_np. By excluding the first column, it selects all rows of the array and all columns starting from index 1. Input features will be assigned to x in the resulting array. The line y equals shifted_df_as_np, 0, extracts the target variable from the array shifted_df_as_np. All rows of the array are selected, but only the first column, index 0, is selected. Assigning the target variable to y, the resulting array contains the input features. The following line retrieves the shapes or dimensions for the arrays x and y. In the x array, the expression x.shape returns a tuple with two values, representing rows and columns. It provides information about the size and structure of the input features. As with y.shape, y.shape returns a tuple with one value, representing the number of elements or rows in y. The size of the target variable is indicated here. Upon executing this code, you split the shifted_df_as_np array into two separate arrays, x and y, representing the input features and target variable, respectively. These arrays can be used for a variety of machine learning tasks, including training models or further analysis. By retrieving the dimensions of these arrays, the x.shape and y.shape expressions can provide insight into their size and structure. By flipping the columns of the x array in reverse order, this code transforms the array. To flip the columns of the array x, the code uses np.flip from the NumPy library. Axis equals 1 specifies that the flipping operation should be applied along the columns. The flipped array is then assigned back to x. It ensures that the flipped array is a separate copy and does not affect the original array x by using the DC function, which is a shorthand for deep copy. This code reverses the order of the columns in the array X. In certain applications, such as time series analysis or sequence modeling, the order of the input features may be significant or dependent. As a result, the flipped array, X, can be used for further analysis or modeling. For dividing data into training and validation sets, this code calculates the split index based on the length of the X array. The line of code split_index equals int len x 0.95 calculates the split index by multiplying x by 0.95. 0.95 represents the proportion of data that will be used for training. Len x returns the number of rows or elements in the array X. When this length is multiplied by 0.95, a fractional index position indicates where training and validation data should be split. After the split index has been determined, it is assigned to the variable split_index, representing the position in the X array where the data will be divided for training and validation. This code determines the index position within the X array that separates the data into two parts. Typically, 95% of the data is used for training, and 5% for testing or validation. Using the split index value, the X array can be divided into separate training and validation sets, allowing for independent evaluations. Separate training and testing sets are created by splitting the X and Y arrays. It selects a subset of rows from the X array, starting at the first row and continuing up to, but not including, the split_index value. A subset of these rows is assigned to the X_train variable, which represents the training set. X_test equals X split_index, selects a subset of rows from the X array, starting at the split_index value and continuing until the end. Input features for testing are assigned to the X_test variable. Similarly, the lines Y_train equals Y, split_index, and Y_test equals Y split_index, also split the Y array. The training and testing sets of the target variable are represented by separate variables Y_train and Y_test. This next line retrieves the shapes or dimensions of the arrays X_train, X_test, Y_train, and Y_test. Using this code, you divide the X and Y arrays into two sets, X_train and X_test for input features, and Y_train and Y_test for target variables. Splits are based on the split_index value, which determines the separation point between arrays. Using the resulting subsets, machine learning models can be trained and tested independently, allowing independent evaluation and validation. The expressions X_train.shape, X_test.shape, Y_train.shape, and Y_test.shape provide information about the sizes and structures of these arrays. For certain machine learning models or algorithms, this code reshapes input features and target variables to match the desired format. This line of code reshapes the X_train array into a three-dimensional array with dimensions, -1, lookback, 1. Based on the array size, the -1 value is automatically calculated as a placeholder. The lookback value represents the number of previous time steps considered, while the 1 indicates that each time step has a single feature. Similarly, the line X_test equals X_test.reshape -1, lookback, 1, ensures that the X_test array is reshaped in the same manner as X_train, ensuring consistency. As follows, Y_train equals Y_train.reshape -1, 1, and Y_test equals Y_test.reshape -1, 1, reshape the Y_train and Y_test arrays, respectively. By converting one-dimensional arrays into two-dimensional arrays with a single column, they effectively create column vectors. The expressions X_train.shape, X_test.shape, Y_train.shape, and Y_test.shape provide information about the shapes and dimensions of reshaped arrays. In this code, the input feature and target variable arrays are modified to match certain machine learning models' expected input formats. When working with specific model architectures, such as recurrent neural networks, RNNs, or convolutional neural networks, CNNs, input data needs to be reshaped. As a result, X_train, X_test, Y_train, and Y_test can be used as inputs to these models. In this code, input features and target variables are converted into PyTorch tensors and their shapes are retrieved. A PyTorch tensor is created by converting the array x_train to torch.tensor x_train. Float. Torch.tensor creates a tensor from the array, and float ensures that the tensor has a floating point data type. This line converts the y_train array into a PyTorch tensor, the same process as for the x_train array. x_test and y_test are converted using torch.tensor x_test. Float and torch.tensor y_test. Float, respectively. x_train.shape, x_test.shape, y_train.shape, and y_test.shape retrieve the shapes or dimensions of the tensors. The code converts input features and target variables into PyTorch tensors, which are multidimensional arrays optimized for numerical computations. PyTorch uses tensors to train and evaluate deep learning models. PyTorch models and operations can use the resulting tensors, x_train, x_test, and y_train. x_train.shape, x_test.shape, y_train.shape, and y_test.shape retrieve the dimensions of these tensors, providing information about their sizes and structures. As a result of inheriting from PyTorch's dataset class, this code defines a custom dataset class called time series dataset. This line of code imports the dataset class from torch.utils.data, which is a base class for creating custom datasets in PyTorch. There are three main methods in the time series dataset class: _init_, _len_, and _getItem_. _init_ is the class's initializer or constructor. The input features and target variables are represented by two arguments, x and y. The input features are assigned to the self.x attribute, while the target variables are assigned to the self.y attribute. _len_ returns the length of the dataset, which corresponds to the number of samples or data points. It returns the length of the x attribute in this case. The _getItem_ method retrieves an item or sample from the dataset based on an index I. A tuple containing the ith element of self.x and self.y is returned. The code creates instances of the time series dataset class named train_dataset and test_dataset after defining the class. Each instance is initialized with the x_train, y_train, and x_test, y_test datasets. This code defines a time series specific dataset class. By using this class, you can encapsulate and organize input features and target variables. Train_dataset and test_dataset instances can be used with PyTorch's data loaders and other utilities for efficient data handling. The code snippet train_dataset refers to an instance of the custom dataset class time series dataset created earlier. It returns the train_dataset object, which represents the training dataset for a time series problem. Within the time series dataset class structure, the train_dataset instance contains the input features and corresponding target variables for the training set. Data loaders, model training routines, or evaluation procedures can use this dataset object as input to various data handling and training processes. With the train_dataset object, you can access and manipulate training data efficiently for time series analysis and modeling. Data loaders are created for the training and testing datasets using the data loader class from the torch.utils.data module. From torch.utils.data import data loader, the data loader class is imported, which is a PyTorch utility for loading and batching data. During training or evaluation, the variable batch_size is set to 16, which indicates how many samples will be processed in each batch. Train_loader equals data loader train_dataset. Batch_size equals batch_size, shuffle equals true, creates a data loader named train_loader for the training dataset. To randomly shuffle the samples within each epoch during training, it takes the train_dataset object and the batch_size value as inputs. During training, this introduces randomness and reduces bias. As with test_loader, data loader test_dataset, batch_size equals batch_size, shuffle equals false, creates a data loader named test_loader for testing. As an input, it takes the test_dataset object and batch_size value, and sets shuffle equals false to maintain the order of samples during evaluation. By doing so, the model's performance can be evaluated consistently and reproducibly. This code creates data loaders for loading and batching data from training and testing datasets. The data loaders can be used in the training and evaluation loops of machine learning models to process data in batches efficiently, improving memory utilization and training efficiency. The train_loader and test_loader objects allow easy iteration over the data during training and evaluation, providing batches of samples each time. The code iterates over the batches of data from the train_loader data loader. The line for batch in enumerate train_loader initiates a loop that cycles over the batches of data in the train_loader. In this case, underscore represents an index or value that is not needed, while batch represents each batch. This line assigns the input features and target variables of each batch to the variables x_batch and y_batch in each iteration. It transfers batch data to the device specified by the device variable, which could be a GPU, CUDA, or CPU. The line print x_batch.shape, y_batch.shape, prints out the shapes and dimensions of x_batch and y_batch. Information about the current batch's input features and target variables is provided here. After the first iteration, the break statement is used to exit the loop. A first batch of data is commonly inspected or some initial checks are performed without iterating over the entire dataset. You iterate over the batches of data in the train_loader data loader by executing this code. Input features and target variables are assigned to x_batch and y_batch for each batch. Printing is then done on the shapes of these batches. By doing this, you can verify the sizes and structures of the data within each batch, which can be helpful for understanding the format and characteristics of the data as well as for initial data exploration and debugging. PyTorch is used in this code to create a custom LSTM, long short-term memory, model. A class called LSTM is defined, inheriting from PyTorch's nn.module class. PyTorch's neural network module can be utilized by the custom class in this way. The LSTM model is initialized in the _init_ method. Input_size specifies the size of the input features, hidden_size specifies the number of hidden units in the LSTM layer, and num_stacked_layers specifies the number of stacked layers in the LSTM layer. To properly initialize the LSTM class, the super_init_ line calls the parent class constructor. Based on the arguments provided to the _init_ method, the hidden_size and num_stacked_layers attributes are set. This line creates an instance of the LSTM layer, using PyTorch's nn.lstm class, using input_size, hidden_size, num_stacked_layers, batch_first equals true. To expect batch first input data, it specifies the input size, hidden size, number of stacked layers, and batch_first equals true. This line creates a linear layer using the nn.linear class by setting self.fc equals nn.linear hidden_size, 1. The input size is specified as hidden_size and the output size is 1. LSTM forward passes are defined by the forward method. The computations are performed on the input tensor X and the output is generated. As part of the forward method, the batch size is determined by the formula batch_size equals x.size 0. It is necessary to initialize the hidden state and cell state of the LSTM layer as tensors of zeros by using the following formula: h0 equals torch.0 self.num_stacked_layers, batch_size, self.hidden_size. To device and c0 equals torch.0 self.num_stacked_layers, batch_size, self.hidden_size. To device. A tensor X is passed through the LSTM layer using out equals self.lstmx, h0, c0. The forward pass of the LSTM layer is computed here, resulting in the output tensor out. The output tensor is then passed through the linear layer using self.fc, out, -1, smiles. LSTM outputs are indexed by the time step of last time step, and then mapped to a single output using the linear layer. The forward method returns the output tensor out. In this example, model is an instance of the LSTM class with input size 1, hidden size 4, and 1 stacked layer. A model is moved to the specified device, which could be a GPU, CUDA, or CPU, Using PyTorch, this code defines a custom LSTM model architecture. For time series forecasting or sequence modeling, this model can be used. Model represents the configured LSTM model, ready for further training, evaluation, or prediction. Train_1_epoch defines a function that trains the model for a single epoch or iteration. Train_1_epoch starts by setting the model to training mode with model.trainTrue. Activating certain operations, such as dropout, ensures that the model is ready for training. The line printf epoch +1, is used to print the current epoch number, which shows how the training process is progressing. Running_loss is initialized to 0.0, which keeps track of cumulative loss across batches. As a result, the function enters a loop that iterates over the batches of data in the train_loader. In each batch, input features and target variables are assigned to x_batch and y_batch, respectively, and are transferred to the specified device using toDevice. In order to obtain the predicted output, the model is called with x_batch as input. Using the specified loss function, the loss between the predicted output and the target variables is computed and added to the variable running_loss. For the next step of backpropagation, the optimizer's gradients are reset to 0 using optimizer.0_grad. To compute and store the gradients of model parameters, the loss is backpropagated through the model using loss.backward. As a result, the model's parameters are updated using optimizer.step, applying the computed gradients. The conditional statement, if batch_index %100 equals 99, checks if the current batch index is a multiple of 100 within the loop. The average loss over the previous 100 batches is printed using this condition. The average loss is calculated by dividing the running_loss by 100 and printed along with the current batch index. This statement is added after the loop to improve readability by adding an empty print statement. This code defines a function that iterates over the training data in batches to train the model for one epoch. In each iteration, the model performs forward and backward propagation, updates the parameters, and calculates the loss. To provide feedback on the training progress, the function prints the average loss every 100 batches. Using the testing data, this code defines a function called validate_1_epoch that validates or evaluates the model for one epoch. Validate_1_epoch begins by setting the model to evaluation mode using model.trainFalse. In this way, operations such as dropout are deactivated, which ensures the model is in the appropriate evaluation mode. As part of the validation process, a variable called running_loss is initialized to 0.0, which keeps track of the cumulative loss across batches. In the loop, the function iterates over the batches of data in the test_loader. The input features and target variables are assigned to x_batch and y_batch, respectively, and are moved to the specified device using toDevice. With x_batch as input, the model produces its output. During the validation phase, the torch.no_grad context manager is used to temporarily disable gradient calculation and backpropagation. In the running_loss variable, the loss between the predicted output and the target variables is calculated using the specified loss function. The average loss across the batches is calculated by dividing running_loss by the number of batches in the test_loader. After printing the average loss using the print function, we see the validation loss for the current epoch. To improve readability, we use the following lines to provide visual separation and add new lines. Using this code, you define a function that validates or evaluates the model for one epoch using the testing dataset. It iterates over the testing data in batches, calculates the loss between the predicted output and the target variables, and accumulates the loss. During validation, the average loss is calculated and printed, providing feedback on the model's performance. Using a given learning rate, loss function, and optimizer, this code trains and validates the model. The variable learning_rate is set to 0.001, which is used to determine how frequently the optimizer updates the model parameters. Num_epochs is set to 10, indicating the total number of passes over the training data. Loss_function specifies the mean squared error, MSE, loss, which measures the discrepancy between predicted and target values in regression problems. As arguments, the model parameters and the learning rate are passed to the optimizer using the ATOM optimization algorithm. ATOM optimizers are popular for training neural networks because they combine adaptive learning rates and momentum. As a result, the loop for epoch in range num_epochs iterates over the range of epochs, starting from 0 and ending at num_epochs 1. In each epoch, the train_1_epoch function is called to train the model. During training, this function performs forward and backward propagation, updates the model parameters, and prints the average loss for each batch. Using the testing data, the validate_1_epoch function evaluates the model's performance after one epoch of training. Calculates and prints the average loss for the testing dataset. This code trains and validates the model for the specified number of epochs. Each epoch, the model is trained using training data, and its performance is evaluated using testing data. Over time, the model learns and improves as it repeats the process for the designated number of epochs. The code generates a plot comparing the actual and predicted values of the close variable. With torch.no_grad, gradient calculation and backpropagation are disabled. In this case, we only want to make forward passes through the model without updating any parameters or calculating gradients. The line predicted equals model x_train.toDevice. To CPU.NumPy applies the train model to the training data in order to determine the predicted values for the close variable. A tensor is moved to the specified device, GPU or CPU, using the toDevice method, and a tensor is retrieved using the toCPU method for compatibility with NumPy. For easier plotting, the predictions are converted to a NumPy array. In the following lines of code, a line plot is created using the matplotlib library. A plot of the actual close values from the training dataset can be seen by plotting plt.plot_y_train, label equals actual close, while a plot of the predicted close values based on the model can be seen by plotting plt.plotPredicted, label equals predicted close. plt.labelDay and plt.labelClose provide labels for the x-axis and y-axis, respectively. By calling plt.legend, a legend is added to the plot, which indicates what the actual and predicted values are. To display the plot, plt.show is called. This code generates a line plot comparing the actual and predicted values of the close variable for the training dataset. By observing how well the predicted values match the actual values, you can assess the model's performance. A transformation is applied to the predicted values for the training dataset obtained from the model in this code. This line flattens the predicted values obtained from the model, converting them from a multidimensional array to a one-dimensional array. In order to facilitate further processing and calculations, this is done. It creates an array of zeros called dummies with a shape determined by the number of samples in the training dataset and the lookback value plus 1. A line that reads dummies, 0, equals train_predictions assigns the train_predictions array to the first column of the dummies array. In the first column, the predicted values replace the zeros. Using the scalar object, the following line applies the inverse transformation to dummies. During this step, the dummies array is converted back to its original scale, reversing any scaling or normalization applied earlier. The line train_predictions equals DC dummies, 0, extracts the first column of the dummies array and assigns it to train_predictions. As a result, train_predictions contains the processed and transformed predicted values. This code transforms and processes the predicted values for the training dataset. As soon as the values are flattened, they are assigned to the dummies array, inversely transformed to their original scale, and then extracted into train_predictions. Predicted values for the training dataset are stored in the train_predictions array, ready for further analysis and evaluation. The target variable values for the training dataset are processed and transformed in this code. It generates an array of zeros called dummies with a shape determined by the number of samples in the training dataset and the lookback value plus 1. The line dummies, 0, equals y_train.flatten assigns the flattened target variable values to the first column of the array dummies. Using this method, the zeros in the first column are replaced with the values of the target variables. Using the scalar object, the following line applies the inverse transformation to dummies. By reversing any scaling or normalization applied earlier, it returns the dummies array to its original scale. Assigning values to new_y_train is done by dividing new_y_train by the values in the first column of the array dummies. In this way, new_y_train contains the training dataset's processed and transformed target variable values. This code transforms the target variable values for the training dataset. Using the scalar object, the values are inverse transformed to their original scale, and then extracted into new_y_train. For further analysis or evaluation, the new_y_train array contains the processed and transformed target variable values for the training dataset. After processing and transforming the training dataset, this code generates a plot that compares the actual and predicted values of the close variable. It plots the new _y_train array, which represents the processed and transformed actual values of the close variable from the training dataset. Using the function plot.plot train_predictions, label equals predicted close, the train_predictions array is plotted. This array contains the processed and transformed predicted values for the close variable from the training dataset. Afterwards, plot.label day and plot.label close set the labels for the x-axis and y-axis of the plot, respectively, indicating the day and the value of the close variable. Adding a legend to a plot by calling plt.legend adds labels for actual and predicted values to the plot. The plot is displayed by calling plt.show. This code generates a line plot that visually compares the processed and transformed actual values, new_y_train, and predicted values, train_predictions, of the close variable. With this plot, you can observe how well the predicted values match the actual values, taking into account any preprocessing or transformations performed. The code applies some transformations to the predicted values for the testing dataset obtained from the model. The line test_predictions equals model x_test.toDevice. Detach. CPU. NumPy. Flatten applies the train model to the test data. A device, GPU or CPU, is specified for moving the x_test data. Using the detach method, the output tensor is detached from the computation graph, preventing further gradient tracking. The output tensor is then moved to the CPU using CPU, and the predictions are flattened into one-dimensional arrays using flatten. This line creates an array of zeros called dummies with a shape determined by the number of samples in the test dataset and the lookback plus 1 value. Using the test_predictions function, it is possible to assign the predicted values to the first column of the dummies array. In the first column, the predicted values replace the zeros. Using the scalar object, the next line uses the inverse transformation on dummies. The code reverts any scaling or normalization applied earlier to the dummies array. In this case, test_predictions is set as DC dummies, 0, and the first column is taken as dummies, 0. The test_predictions variable contains the processed and transformed predicted values for the testing dataset. This code transforms and processes the predicted values for the testing dataset. Model values are assigned to the dummies array, inverse transformed to their original scale using the scalar object, and then extracted into test_predictions. Test_predictions contains the processed and transformed predicted values for the testing dataset, ready for analysis and evaluation. In this code, the target variable values for the testing dataset are processed and some transformations are applied. The line dummies equals np.zeros x_test.shape0, lookback plus 1, creates an array of zeros called dummies with a shape derived from the number of samples in the test dataset and the lookback value plus 1. In the dummies array, the flattened target variables values are assigned to the first column by y_test.flatten. The target variable values are replaced by zeros in the first column. Using the scalar object, the following line applies the inverse transformation to the dummies. The code restores the dummies array to its original scale, reversing any scaling or normalization applied earlier. In this line, we extract the values from the first column of the dummies array and assign them to new_y_test. In this way, new_y_test contains the values of the processed and transformed target variables. As a result of executing this code, the target variable values for the testing dataset are processed and transformed. Using the scalar object, the values are inverse transformed to their original scale and extracted into new_y_test. New_y_test contains the processed and transformed target variable values for the testing dataset, ready for further analysis. Using this code, a plot is generated that compares the actual and predicted values of the close variable for the testing dataset. In this example, the line plt.plot new_y_test, label equals actual close, plots the new_y_test array, which represents the processed and transformed actual values of the close variable from the testing dataset. This line plots the array test_predictions, which contains the processed and transformed predicted values of the close variable for the testing dataset. Next, we will set the labels for the x-axis and y-axis of the plot, specifying the day and the value of the close variable, respectively. This statement adds a legend to the plot, labeling the actual and predicted values. The plot is displayed by calling plt.show. Executing this code generates a line plot that visually compares the processed and transformed actual values, new_y_test, and predicted values, test_predictions, of the close variable. By observing how well the predicted values align with the actual values, you can evaluate the performance of the model,